So I got a request from one of your classmates that they did not know how to do some of the practice problems or some of the problems in your Chapter 5 homework, and they did not see resources on my YouTube page that showed how to do them. So, I just said, hey, send me an email with those problems and I will work through something very similar to it. Okay, so one of the questions that they requested was this question right here. This is using the compound BaOH2 as a strong electrolyte. Determine the concentration of each of the individual ions in a 0.800 molar BaOH2 solution. Okay, so what this tells us is this tells us the concentration of BaOH2, and it is equal to 0.8 molar. Now, one thing that I'd like you to think about is what BaOH is? Well, it's an ionic compound. What it is going to do is it's going to dissociate into Ba2 plus and 2 OH minus ions. Okay, so what that means is if you have 1 mole of BaOH2, then you'll have 1 mole of Ba2 plus ions and 2 moles of OH minus ions. Likewise, if you have 50, let's say 52 moles of BaOH2, then you'd have 52 moles Ba2 plus and 104 moles of OH minus ions. Okay, so that's how you need to set this up, because you have a 2-to-1 ratio in your compound right here. 1 mole of this for every 2 moles of this. Okay, so what that means is your concentration of BaOH2 is 0.800 molar. Well, then that's going to give you the precise concentration of Ba2 plus ions. But what does that mean about our OH ions? So I'm going to go ahead and answer this as 0.800, but I'm going to leave you guys to figure out the rest of it with the OH minus ions. All right, moving on. All right, so this problem right here is a little bit complicated and pretty tricky and pretty challenging. So, but let's get down to it. Liquid sodium is being considered as an engine coolant. How many grams of liquid sodium are needed to absorb 5.40 megajoules of energy in the form of heat if the temperature of the sodium is not to increase by more than 10 degrees Celsius? Use Cp, which is a heat capacity, of 30.8 joules per Kelvin mole, okay? And that is for liquid heat at 500 Kelvin. Now this throws a lot of numbers at you, but what this ultimately is asking is how much liquid sodium can absorb 5.40 megajoules of energy and not change, or your temperature not change by more than 10 degrees. So what this ultimately boils down to is this is your amount of heat, and your delta T, your change in temperature, is 10 degrees, 10.0 degrees Celsius. Okay. Now, the way that you need to approach this is you need to use the equation Q equals mc delta T. Okay. Now, Q is going to be the heat. M is going to be the mass. C is the heat capacity. And delta T is your change in temperature. We actually have a number of these values, but there's one value that we need to manipulate a little bit, and that is that Cp. We're presented with molar heat capacity. What we need to do is we need to convert that into specific heat capacity. Molar Cp converted to specific heat capacity. Now the difference here is the units. Molar heat capacity is joules per Kelvin moles, and specific heat capacity is joules per gram Kelvin. So essentially what this means is that if you have 1 mole, or what we're presented with, if you have 1 mole of sodium, liquid sodium, well then you need 30.8 joules of energy to change the temperature of 1 mole by 1 degree. Okay, what we need to do is basically convert this so that rather than this mole factor in the denominator, we have a mass. Okay, so in order to do that, so we need to basically take this number, this 30.8 joules per mole Kelvin, and all that we need to do is figure out, well, what is the relationship between 1 mole of liquid sodium and grams of liquid sodium? Well, that happens to be 23 grams. So all that we need to do is basically take this variable right there, and rather than it being 1, we need to sub in 23. And that will give us a value of approximately 1.34 joules per gram Kelvin. Okay, so that means you need 1.34 joules of energy to convert 1 gram of liquid Kelvin to heat 1 gram of liquid sodium 1 degree Kelvin. Okay, so now what I'm going to do is I'm going to erase a little bit of this. So erase this so that I can basically plug it back in and manipulate my equation a little bit. Okay, so erase these. Alright, so then what I'm solving for ultimately is this value right here, mass. So all that I need to do is take my heat, Q, and manipulate this equation so that I have C delta T in the denominator and then mass by itself. Because now I have my specific heat capacity, my C value in the units of grams. So that is something that I don't need to worry about reconciling anymore. The only thing that I need to do is take this 5.40 megajoules and convert it to joules, because if I look at my specific heat capacity, I'm talking about that in joules as well. And all that is I'm moving the decimal place 6 places to the right. So I'm looking at 5.40 times 10 to the 6th joules. So all that I'm going to do is, now I've got it all in the units that I want. So I've got 5.40 times 10 to the 6th divided by, well, 1.34 times my change in temperature, which was 10.0. Solve for that. That is going to end up being the mass that you need. Okay, what I would do is before I plug my numbers in, make sure that I have rounded to the correct number of significant figures and everything like that, because as you can see, each one of these numbers here has 3 significant figures, so you want to make sure that, well, your final answer has the correct 3 significant figures. But I'm going to leave that. That's how you set this problem up. All right, so this is the third question that one of your classmates asked me to go ahead and demonstrate how to do. And this is a good one. It's totes tricky, but totes doable. Okay, so this question reads, in a constant pressure calorimeter, 70 milliliters of a solution of barium hydroxide, that solution has a concentration of 0.320 molar, was added to 70 milliliters of 0.640 molar HCl. Okay, the reaction caused the temperature of the solution to rise from 21.43 degrees to 25.8 degrees Celsius. Okay, so that right there, that's telling me we've got a change in temperature. Okay, I just want to keep note of that. If the solution has the same density and specific heat as water, 1 gram per milliliter and 4.18 joules per gram degree Celsius, respectively, what is the delta H for this reaction per mole of H2O produced? Assume the total volume is the sum of the individual volumes. Okay, so what we're looking at here, and the first thing that we have to do is come up with our balanced chemical reaction. We are looking at a reaction between barium hydroxide and HCl. Okay, now this is a metathesis reaction. It's also a neutralization reaction. It's also a double displacement reaction. It is all of those things. And yeah, it's just all of those things. Okay, so what we've got is the hydroxide ion and the hydrogen ion. They're going to come together and make H2O.
That's super fun.
We will also make, well, let's think about this. Barium on the periodic table is in group 2, so that is a +2 cation. Hydroxide is a -1, hence the 2 subscript there. So we are going to make water and BaCl2. Okay, now we need to balance this out. So what I'm going to do is I'm going to balance the chloride ions. I'm also going to go ahead and erase some of these doodles that I had a moment ago. Done, 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 done. Okay, so I'm going to balance my chlorides. I'm going to put a 2 coefficient in front of the HCl. I've balanced out my chlorides. Okay, so now bariums. There's one barium, there's one barium. We're balanced. Hydroxide. Well, I've got an O and an H in my H2O. I've also got one of my H's over here. Okay, so I've got 2 hydrogens. This brings me 4 hydrogens. Here's 2 hydrogens. But I also have 2 oxygens. So I'm going to put a 2 out in front of here. Okay, so now I've got, let's balance out our hydrogens and oxygens.
Yeah,
Here's 2 oxygens, 4 hydrogens. Over here I've got 4 hydrogens.
The blonde lady, she's like, I have 3 boys. I
2
oxygens.
And that basically sums everything up with respect to my balanced chemical reaction.
To go to Vegas.
Okay, so I've got all of those different things balanced out. That's my balanced chemical reaction. Now, what I'm looking at here is ultimately, I'm looking at a change in temperature. Okay, so I've got a change in temperature. I've got a delta H here. What I want to do is I want to calculate. I need to go ahead and calculate my number of moles. Okay, so I know that I had a 70 milliliter solution with a concentration of 0.320 moles of barium hydroxide.
I felt that way every time.
Whenever I plug that in,
there's like a bunch in there.
I have
and then I'm like, oh,
0.0224 moles of BaOH2. Okay, now whenever I take my 70 milliliters of 0.640 molar HCl, I have, and I've already done the math for this separately, I have 0.0448 moles of HCl. Okay, so the way that I did that was 0.070 liters times 0.320 molar equals 0.0224, and then I did the exact same thing for the other. So what this actually shows me is this is a perfect example of I have no limiting reactant or anything like that. Now what ultimately this means is I'm going to be able to produce 0.0448 moles of H2O. The reason that I know that is because I've got a 1-to-1 molar ratio of HCl to H2O. So it's actually a 2-to-2, but it's the same as a 1-to-1 because however many moles of HCl are going to be utilized, I'm going to have the exact same number of moles of H2O that are actually produced. Okay, so I bring that up because this question is asking me, what is my delta H per mole of H2O produced? Okay, so what I want to do is I want to plug in my equation, Q equals mc delta T. Okay, I'm plugging this in because I know some pieces of information already. For instance, do I know my heat capacity? Yes, I do. It is 4.184 joules per gram degree Celsius. Okay, do I know my change in temperature? I absolutely do. And I know that that is going to give me, sorry, my change of temperature is 25.4, or 25.8 minus 21.43. Okay, I've got my calculator right here. I'm going to plug that in. 25.8 minus 21.43 equals 4.37. Okay, so I have a change in temperature of 4.37 degrees. Now the last thing that I need to know is my M value. Okay, that's going to be my mass. Well, I have the mass, or I'm sorry, I have the total volume that I'm using, because what I'm doing is I'm adding 70 milliliters of a solution. I'm trying to find my cursor. 70 milliliters to 70 milliliters of another solution. So my total volume
people are always going to find something
is
to judge you about, so
my
whatever it is.
sum of my individual volumes. So that is 140 milliliters. And I know from my density that this is 140 grams. Because my solution is has a density of 1 gram per milliliter, I know that my 140 milliliter solution
I think it's like,
has
yeah,
a
it's like
mass
the
of
flip side of
140
the
grams.
exchange.
So I'm going to go
People are
ahead
like,
and
you know.
erase
I mean, and obviously
that,
there's one thing there, so not
and I'm
walk
going
around
to
talking
go
about
ahead
it,
and
but,
plug in grams right here. Now what this is going to give me, when I plug these values in, this is going to give me my Q. That is going to be the heat that is produced in terms, and my units are going to be in joules. And I can do that because, well, at this point in time, that's going to get me like 90% of the way. The last little bit is my units are going to be kilojoules per mole of H2O. So what I'm looking at here is what is the heat that is produced in this given reaction. So I'm going to take 140 times 4.184 times 4.37. That is equal to 2559.78 joules. Okay. Now, one very important thing about this problem is
you did something
we have
wrong.
to think about what's happening. Well, with respect to what's happening what I mean by that is we have to find out if this is a negative or a positive value. Okay. Well, you can deduce that it is a negative value because that is heat that is being released from the system. And we know that because we know that that is released heat because of the fact that what we're seeing is a temperature of our solution increasing. So we're going from 21.43 degrees to 25.8 degrees. So that heat is being released, it's being evolved and being released to the outside environment. So that gives us a negative value there. So now all that we need to do is we need to take this negative 25.59, divide it by our total number of moles of H2O, which our total number of moles of H2O happens to be 0.0448 moles. And we learned that because our earlier reaction told us the number of moles of H2O that are produced. So I'm going to divide that 2559 by 0.0448, and that's going to give me a value of, here's my answer, my negative 57, and that's 57,137.75. Now before I go ahead and complete my answer, well, this number, what are my units here? The way that I calculated it's joules per mole. So what you have to do with this, joules per mole of H2O, you have to convert this into kilojoules per mole of H2O. Now I'm going to stop right there, but I hope this is helpful, and I wish you the best on the exam tomorrow. Or, well, I wish you the best on the exam whenever you decide to take it. All right, well, thank you very much. Have a good one.